Hi everyone, today we're going to study antiderivative of a function. Let us define antiderivative of a function. A function capital F is an antiderivative of the function small f if capital F prime of x is equal to small f of x for all x in the domain of f. For our example, recall that g of x is equal to x squared and the derivative g prime of x equals 2x. Now, when we have f of x is equal to 2x, the antiderivative is capital F of x is equal to x squared. Note, finding antiderivative is the reverse process of finding derivative. Now, let us go to the general form of antiderivative. In our example a while ago, the function small f of x is equal to 2x. And we say that the antiderivative is capital F of x equals x squared. Because if we take the derivative of x squared, the answer is 2x. Now, there are other antiderivatives for the function 2x. I will write one example. F of x is equal to x squared plus 5. The derivative of this function is 2x. Another example is capital F of x equals x squared minus 7. The derivative of this function is the function 2x. So we see here that these three functions are antiderivatives of the function 2x. So we have this capital F of x plus an arbitrary constant c. This is now what we call the general form of antiderivative. Let us see more sample problems. Find all antiderivatives of the following functions. Our first function here is f of x equals 3x squared. For our solution, we know that the derivative of x cubed is equal to 3x squared. Then, capital F of x is equal to x cubed is an antiderivative of 3x squared. Therefore, every antiderivative of 3x squared is of the form x cubed plus c. So our final answer here is the capital F of x is equal to x cubed plus c. Next is the function f of x equals 1 over x. We know that the derivative of ln x equals 1 over x. Then, the capital F of x is equal to ln x is an antiderivative of 1 over x. Therefore, every antiderivative of 1 over x is of the form ln x plus c. So our final answer for the antiderivative is capital F of x is equal to ln x plus c. Function c is f of x equals cosine x. We know that the derivative of sine x equals cosine x. It means the capital F of x equals sine x is an antiderivative of cosine x. Therefore, every antiderivative of cosine x is of the form sine x plus c. So our final answer is capital F of x equals sine x plus c. function for f of x equals e raised to x. We know that the derivative of e raised to x is equal to e raised to x. Then, the capital F of x is equal to e raised to x is an antiderivative of e raised to x. Therefore, every antiderivative of e raised to x is of the form e raised to x plus c. So our final answer is capital F of x equals e raised to x plus c. These are our final answers. Today we're going to study indefinite integrals. Let us define indefinite integrals. Here, we introduce notation for antiderivatives. If capital F is an antiderivative of the function f, we say that capital F of x plus c is the most general antiderivative of function small f. And we write the integral of f of x dx equals capital F of x plus c. In this expression, the symbol here is what we call integral sign. The f of x is the function and we call it integrand. The variable x is the variable of integration. The expression integral of f of x dx is what we call now indefinite integral of the function f. Note that integration is the process of finding integral of a function. Thus, it is the reverse of differentiation. Let us see some formulas of indefinite integrals. The first is what we call integral of a constant. We see here we have integral of k dx. K here is a constant. And the answer is kx plus c. Let's see one example. And this is the integral of 8 dx. This is equal to 8x plus c. This is the final answer. Second formula is the power rule of integral. This is referring to the integral of x raised to power n dx. And this is equal to the x variable raised to a power n plus 1. All over, the denominator is that same n plus 1. And then plus c. Take note that the n here should not be equal to negative 1. One example here is the integral of x raised to 10 dx. This is equal to the x is now raised to 10 plus 1 all over the denominator 10 plus 1 and then plus c. Simplifying this expression now, we have x raised to 11 over 11 plus c. This is our final answer. Third formula, when we have the integral of 1 over x dx. This is now the expression when the value n is equal to negative 1. This is equal to the ln of the absolute value of x, then plus c. Let us see some properties of indefinite integrals. Let capital F and capital G be antiderivatives of function small f and function small g, respectively, and let k be any real number. The first property is about sums and differences. So this is the expression, the integral of two functions, let's say f of x plus or minus g of x dx, and this is equal to this expression. What we're doing here is taking the integral of each of the function here with respect to x, and then the final answer will be capital F of x plus or minus capital G of x, and then plus c. Second property is about constant multiples. The integral of k f of x dx. This is equal to k is moved out from the integral, so we have k times the integral of f of x dx. And then we can simplify this into k times capital F of x plus c. Today we're going to evaluate indefinite integrals. First, let us make a review. In our recent video, we studied about integration formulas, and these are the integral of a constant, the power rule of integral, and the integral of 1 over x dx. Also, we studied about properties of indefinite integrals. These properties are the integral of sums and differences, and the second is the integral of constant multiples. On this video, we're going to use those principles to evaluate integrals. In here, we have 5 integrals to evaluate. Let's begin with the number 1. That is the integral of 1 over x raised to 8 dx. In here, we're going to rewrite the expression as the variable x with negative exponent. So we have the integral of x raised to negative 8 dx. And from here, we're going to use the power rule. This is now equal to x raised to negative 8 plus 1 all over the denominator is negative 8 plus 1. Simplifying our exponent, the negative 8 plus 1 is negative 7. So we have x raised to negative 7 all over the denominator is also negative 7. We can simplify this expression into negative of 1 all over 7x raised to 7, and then we will add the plus c. This is now the final answer. Number 2, the integral of the square root of x dx. This time, we're going to rewrite this expression into x with fractional power. So we have the integral of x raised to 1 over 2 dx. And from here, we're going to use the power rule. So we have now the x raised to 1/2 plus 1 all over the denominator is 1/2 plus 1. The 1/2 plus 1 is equal to 3 over 2. So we have now x raised to the power 3 over 2 all over 3 over 2. We can simplify our denominator here by flipping it up. So we have now 2x raised to 3 over 2 all over 3. We can return this x with fractional exponent into radical expression. So we have now 2x square root of x all over 3. Then we will add the plus c. This is now the final answer. Example 3. The integral of the polynomial 5x cubed minus 7x squared plus 3x plus 4 dx. From here, we're going to show that we're going to take the integral of each of the terms of the polynomial. So we have the integral of 5x cubed dx minus the integral of 7x squared dx plus the integral of 3x dx plus the integral of 4 dx. We can see that the first three integrals have constant with some variable x. We can move the constant outside the integral sign. So we have this constant 5 comes out now. This constant 7 comes out of the integral. The constant 3 comes out of the integral. And then we will apply the power rule here, here, and here. While the integral of 4 dx, we will apply the integral of a constant. So we have now 5x raised to 4 all over 4 minus the 7x raised to 3 over 3 plus the constant 3 and then the x with power 2 over 2 plus the 4 with the x, and then we will add the plus c. This is now the final answer. Example 4. The integral of the product x plus 2 times x minus 3 dx. In here, we are going to evaluate the product first. We have the integral of the polynomial x squared minus x minus 6 dx. This is the product of our x plus 2 times x minus 3. From here, we're going to show that we're going to take the integral of each of the terms. So we have the integral of x squared dx minus the integral of x dx and minus the integral of 6 dx. Getting the integral of each of the terms, we have now x cubed over 3 minus x squared over 2 minus 6x, and then we will add the plus c. This is the final answer. Example 5. The integral of the quotient x cubed plus 2x squared minus x all over x squared and then the dx. What we're going to do here is to distribute the denominator to each term of numerator, and then we will simplify. So we see here the integral of x cubed over x squared plus the 2x squared over x squared minus the x over x squared, and the dx is here outside. Simplifying each fraction, we have now the integral of x plus 2 minus 1 over x, and then dx. So we have the integral of x dx plus the integral of 2 dx minus the integral of 1 over x dx. Evaluating the respective integrals now, we have the x squared over 2 plus 2x minus the ln of the absolute value of x, and then we will add plus c. This is now the final answer. Today we're going to study integration formulas. We said that integration is the reverse process of differentiation. Thus, we shall present integration formulas in relation to differentiation. Our first derivative is for kx, and this is equal to k. Now, we have the integral of k dx equals kx plus c. The derivative of x raised to n equals n times x raised to the power n minus 1. This is what we call the power rule of derivative. Now, we have the integral of x raised to n dx. This is equal to x raised to the power n plus 1 all over the denominator n plus 1, then plus c. This is now called the power rule of integral. The derivative of ln of the absolute value of x equals 1 over x. Now, the integral of 1 over x dx equals ln of the absolute value of x plus c. The derivative of e raised to x equals e raised to x. The integral of e raised to x dx equals e raised to x plus c. The derivative of a constant a raised to x equals a raised to x times ln of a. The integral of a raised to x dx equals a raised to x all over ln of a, then plus c. The derivative of sine x equals cosine x. Now, the integral of cosine x dx equals sine x plus c. The derivative of cosine x equals negative sine x. The integral of sine x dx equals negative cosine x plus c. The derivative of tangent x equals secant square x. The integral of secant square x dx equals tangent x plus c. The derivative of cotangent x equals negative cosecant square x. The integral of cosecant square x dx equals negative cotangent x plus c. The derivative of secant x equals secant x times tangent x. The integral of secant x times tangent x dx equals secant x plus c. The derivative of cosecant x equals cosecant x cotangent x. The integral of cosecant x times cotangent x dx equals negative cosecant x plus c. The derivative of sine inverse x equals 1 over the square root of the quantity 1 minus x squared. The integral of 1 over the square root of the quantity 1 minus x squared, then dx equals sine inverse x plus c. The derivative of tangent inverse x equals 1 over x squared plus 1. the integral of 1 over the quantity x squared plus 1 dx equals tangent inverse x plus c. The derivative of secant inverse absolute value of x equals 1 all over x, the square root of the quantity x squared minus 1. The integral of 1 all over x times the square root of the quantity x squared minus 1 dx equals secant inverse of the absolute value of x plus c. Today we're going to evaluate more indefinite integrals. Let us make a review first. In our last video, we studied about integration formulas. Also, we studied about properties of indefinite integrals. Now, we're going to evaluate the following integrals using the formulas and also the properties of indefinite integrals. We have here 5 sample problems. Let's begin with problem number 1. Let us evaluate the integral of the square root of x, this quantity is raised to 3, dx. For our solution, let us rewrite our integrand into fractional exponent. So we have here the integral of x raised to 3 over 2 dx. From here, let us use the power rule of integral. The formula is here. So we have now x raised to 3 over 2 plus 1 all over 3 over 2 plus 1. This 3 over 2 plus 1 is equal to 5 over 2. So we can simplify this into x raised to 5 over 2 all over 5 over 2. Simplifying this complex fraction, we can flip our denominator fraction into 2 over 5. So the 2 becomes the coefficient of the numerator. So we have 2x raised to 5 over 2 all over 5. Let us show now that this x raised to 5 over 2 is equal to x raised to 4 over 2 times x raised to 1/2. This expression here can be simplified into x squared. While this x raised to 1 over 2, let us convert this again into radical form. So we have now 2x squared square root of x all over 5. Then we will add the plus c. This is now the final answer. Let us copy this answer opposite problem number 1. Let's go now to problem number 2. The integral of 4 all over the quantity x squared plus 1 dx. In here, we're going to factor out the constant 4 or that numerator outside the integral sign. So we have now 4 times the integral of 1 all over x squared plus 1 dx. We have a formula for this integral, and that is equal to the tangent inverse x plus c. So we can simplify this integral now into 4, that is the constant, times the tangent inverse of x. Then we will add plus c. This is now the final answer. Let us copy this opposite the problem number 2. Let's go now to problem number 3. The integral of tangent x times cosine x dx. We don't have the direct formula for the integral of tangent x cosine x dx. What we're going to do here, we're going to simplify the trigonometric functions here by showing that the tangent x is equal to sine x over cosine x. So we have this expression now. And from here, we can cancel this cosine x along with that denominator cosine x, rewriting our integral. So we have the integral of sine x dx. We have a formula for the integral of sine x dx that is equal to negative cosine x plus c. And this value we will write here. This is now the final answer. We will copy this opposite problem number 3. Let's go now to problem number 4. The integral of the quantity secant square x plus 1 dx. We're going to show that we're going to take the integral of the terms of the functions. So we have the integral of secant square x dx plus the integral of 1 dx. In here, we're going to use two formulas. The integral of secant square x dx, also the integral of the constant k dx. So we have now the tangent x for this integral plus the integral of 1 dx is 1x, or simply x. And then we will add the plus c. This is now the final answer for problem number 4. We will copy this answer opposite problem number 4. Let's solve now for problem number 5. Let us show that we are going to take the integral of each of the term of our function. So we have now the integral of ex dx minus the integral of 3x squared dx plus the integral of cosine x dx. So we're going to use three different integrals here. And these are the formulas that we're going to use. So the integral of ex dx is simply ex minus the constant 3 times x cubed over 3 plus the integral of cosine x is sine x. We can simplify this part by cancelling the 3 and the denominator 3. Rewriting again the answer, we have now e raised to x minus x cubed plus sine x. Then we will write the plus c. This is now the final answer for problem number 5. Let us copy this under problem number 5. Today we're going to study initial value problems. Let us do some introduction first. We're going to solve differential equations. First, let us define differential equations. A differential equation is an equation that relates an unknown function and one or more of its derivatives. The equation dy over dx equals f of x is a simple example of a differential equation. Solving this equation means finding a function y with a derivative f. Thus, the solution is y equals the integral of f of x dx. Later, we will have an answer, and that is capital F of x plus c. This is the general solution. Let's see this example. Solve the differential equation dy over dx equals 6x squared. Let us treat the dy over dx as a common fraction. Let us cross multiply dx to the right side. So we have now dy equals 6x squared dx. And then we will take the integral of both sides. We will have now the integral of dy equals the integral of 6x squared dx. The left side here is simplified into y. This is equal to the integral of the right side. Now let us use our formula of integral to evaluate the right side. So we have now y equals 6 times x cubed over 3. We use the power rule of integral to evaluate x squared. We can cancel the 6 and the 3. So we have now our answer to be y equals 2x cubed plus c. This is now what we call the general solution of the differential equation dy over dx equals 6x squared. Now for the initial value problems, here now is the case. Sometimes we are interested in determining whether a particular solution curve passes through a certain point x sub 0, y sub 0. That is, we are given this notation: y of x sub 0 equals y sub 0. The problem of finding a function y that satisfies a differential equation dy over dx equals f of x with the additional condition y of x sub 0 equals y sub 0 is an example of an initial value problem. This condition here is what we call initial condition. A while ago, we solved this differential equation and we found that the solution is y equals 2x cubed plus c. Now, let us add the initial condition y of 1 equals 5. In this case, we're going to solve for c for this equation. We will do that by substituting the initial condition values. Take note that this notation means there is a point that corresponds to 1, 5. The x value is the 1 and the y value is 5. Let us now substitute these values in this equation. So we have now the y becomes 5 equals 2 times the x cubed now becomes 1 cubed, then plus c. The 1 cubed here is simply 1 and 1 times 2 is 2. So we have this resulting equation. Solving now for c, we transpose 2 to the left side, it becomes minus. So we have 5 minus 2 equals c, and the value of c equals positive 3. Now let us substitute the value of c to the general solution. So we have now this y equals 2x cubed plus the c here becomes 3. This is now our final answer. Example 2. Solve the initial value problem dy over dx equals sine x, and this initial condition y of 0 equals 5. For our solution, we can have the shortcut of y equals the integral of this function sine x, then dx. Solving for the integral, we have now y equals negative cosine x plus c. This is now the general solution. Next step is to find the value of c. Let us substitute the initial value condition. This y of 0 equals 5, which means the point is 0, 5. The x value is 0, while the y value is 5. Let us substitute now in this equation here. So we have 5 for the y equals negative cosine x becomes negative cosine 0, then plus c. The value of cosine 0 is 1, so we have here minus 1. And this negative 1, we will transpose to the left side, it becomes positive. 5 plus 1 equals 6, so the value of c equals 6. Let us substitute the value of c to this general solution. So we have now y equals negative cosine x plus 6. This is now the final answer. I hope you learned something from this video. See you again next time.